Hi, my name is Amay and I welcome you to this video on HTTP Request Smuggling. When I first got to learn about HTTP Request Smuggling, I was pretty confused. I could not wrap my head around this attack. I did not understand why and how this attack worked. And all the content that I watched or I read to understand about this attack, I could not wrap my head around it because the creator of the content assumed that the reader understands HTTP well, but I did not. I understood that to understand HTTP request smuggling well, I need to first understand HTTP. So I went ahead and learned about HTTP, and once I had a clear understanding about the HTTP protocol, it gave me a very beautiful understanding about the request smuggling attack, how it worked and why it worked. So in this video, we are going to look at HTTP request smuggling by first understanding the fundamentals of HTTP that are important for us to understand the request smuggling attack. So let's get started and jump right into it. HTTP was first documented as RFC 1945 in May 1996. HTTP was still in prior use before the release of this RFC, but it wasn't formally documented. So the version that was used before this RFC was dubbed as version 0.9. The most important thing that we need to understand in the context of request smuggling is that HTTP 1.0 required the client to establish a new TCP connection for every individual HTTP request that the client sent to the server. So say for example, if your browser was loading a web page with 30 embedded resources such as images, style sheets, or scripts, your browser will have to make 30 individual TCP connections with the server to load all these resources on your web page. Now this was proving to be a major overhead on the entire internet infrastructure back when the internet was still very nascent and bandwidth was not very cheap. So this problem was partly solved by HTTP 1.1, which was released in 1999 as RFC 2616. HTTP 1.1 introduced the concept of keep alive connections. HTTP 1.1 was built to communicate over a single persistent TCP connection by default. What it meant was that clients were no longer required to make a new TCP connection for every HTTP request they sent to the server. At the server side, what the server did was when a new HTTP request was received from the client, after the request was completed, the server did not immediately close the TCP connection because it expected that the client was going to send more HTTP requests over the same TCP connection. And that was a default behavior of HTTP 1.1. Now this default behavior could be overridden by the clients. Clients could indicate to the server that they do not intend to send multiple HTTP requests over a single TCP connection by including the connection header in their request, which was set to the value of close. So the header read connection close. You could have come across this header usually when intercepting HTTP traffic in Burp or a similar proxy. In HTTP 1.1, clients could also send multiple requests to the server without first waiting for the server to respond to the earlier HTTP request. So they could send HTTP requests one after another, and the response could be handled later after the server has sent the response separately. This was known as HTTP pipelining. Now, when I learned about this feature of HTTP pipelining and how HTTP 1.1 allowed for such efficient communication with the server, I questioned myself that if this feature is so useful, why do I always see the connection close header in my HTTP traffic whenever I inspect it? Why is my browser not using HTTP effectively and using pipelining by default? On further reading, I realized that although HTTP provides this very useful feature of pipelining to send requests back to back, it is not used by modern browsers because of buggy proxy servers and the issue of head-of-line blocking. Let me explain to you what head-of-line blocking means. You see, when HTTP 1.1 pipelining is used, the requests are processed by the server in a first-in, first-out manner, and the responses that are sent back to the client, the sequence of the responses matter. So the server has to send the responses back to the client in the exact sequence in which they were received. So imagine if you had two requests back to back, in which the first request was going to take some time at the server end, and the second request was a very tiny request which was supposed to send back a few bytes of data. But until and unless the server has not responded to the first request, which is going to take some time at the server end, the second request is going to wait at this on the server end because the first request the larger request has to first be sent to the client to maintain the sequence. So this is head of line blocking. This issue of head of line blocking nullifies the speed advantage that is provided by HTTP pipeline. This issue has been partly addressed in HTTP version 2.0 using multiplexing, which we can discuss in another video. That brings me to the most important question. Where is pipelining used? If it's not used in our browsers effectively, where does HTTP pipelining occur? So HTTP pipelining is majorly used by front-end servers to talk to back-end servers. The front-end server can either be a load balancer, a caching server, or a reverse proxy server, or it can also be a server belonging to a content delivery network. Now what the front-end server's job is, its job is to take the HTTP request first that is coming in from all clients all over the internet, and based on the rules configured on the front-end server, it will either modify the request header slightly or add its own headers and send it back to the appropriate backend server based on the configured rules on the front-end server. Now, the front-end servers are handling hundreds to thousands of HTTP requests per second. They have to work very efficiently. And since as we are talking to the front-end servers over HTTP, the front-end server and the back-end servers also talk over HTTP. So if they were to initiate a new connection for every HTTP request being sent to the backend, it would be a major overhead on the infrastructure and would cause both the front-end and the back-end servers to slow down. So to keep things efficient and to minimize the use of resources, these servers talk over keep alive HTTP connections. They reuse the same TCP connection or use a handful of TCP connections to communicate with each other. In such a setup, it becomes the responsibility of the backend server to figure out where a new HTTP request begins and where it ends. So how does the backend figure this out? To understand this, we need to understand the structure of an HTTP request. This is what a typical HTTP post request looks like. The first line of an HTTP request is known as the request line. The request line is made up of three parts. The first part is the HTTP method, which can be a get, put, post, patch, delete, etc. What follows after the method is the path, and after the path you have the HTTP version number. After the request line, you have the HTTP headers. HTTP headers convey important information to the server about the request that tells the HTTP server how to pass this message in a way that is consistent with the RFC. After the headers, you see an empty line, and what follows after the empty line is the request body. But that's not all. There are characters within the HTTP request that are not printable, and hence you cannot see them in this sample HTTP request shown over here. But these non-printable characters are key to the functioning of HTTP correctly. So let's look at how the HTTP request looks with these characters displayed. This \r and \n characters that you see on your screen are known as carriage return and line feed characters. These characters denote the end of line within an HTTP request. The listener component of an HTTP server or a web server is responsible for reading the HTTP request coming into the server, interpreting it correctly, and then passing the control to the relevant port block for execution of intended instructions on the server. The listener component of the web server has to do this in a manner that is consistent with the RFC, and the HTTP listener reads the request character by character. So how does the listener correctly interpret the HTTP request? To understand it, let's try to mimic the HTTP, being an HTTP listener ourselves. So let's look at the request that is on the screen. When the HTTP listener comes up and it starts listening, right? It's listening for something. So what is it listening for? It is looking for a pattern. It is looking for the start of a new HTTP message that is coming in from a client. So in this case, whenever an HTTP request is received, the listener should first receive the request line. So it looks for the pattern of a request line. It looks for a pattern which follows the pattern which we saw earlier, that is a method followed by a path followed by HTTP version. So as soon as it receives this pattern, it understands that this is a start of a new request, and this line ends with a CRLF. So when it receives the first request line, it starts listening for the next component of the HTTP request, that is the HTTP headers. Now the HTTP headers also follow a common pattern, and that pattern has the structure. It starts with the name of the header, followed by a colon and a space, and then the value of the header. So the HTTP listener will start reading the headers one by one until it reaches a line which is an empty line. It has nothing but a single CRLF. This denotes to the server or to the listener that the HTTP headers have now completed. The client has sent all the HTTP headers to the server. And it's the listener's job now to read all the headers, to go through all the headers and interpret the request and understand how it is going to handle the request body and what it is going to do with the request. Now the most important header in the HTTP request that you can see on the screen is the content length header. The content length header tells the server that the content that the client has sent in the message body, what is the size of the content, how many characters or how many bytes has the client sent. As you remember, we spoke earlier that it is the responsibility of the backend server to understand where a message begins and where it ends. So this content length header helps the server understand that the message will end after it has received 5 bytes of data from the client. So because the content length in the example HTTP request on the screen is set to the value 5, it indicates to the server that the client has sent 5 bytes of data to the server. So the request body of our HTTP request contains the word hello, which is made up of 5 ASCII characters, and each ASCII character is made up of 1 byte. So it has sent 5 bytes of data to be handled on the server end. And once the server has read these 5 bytes of data, it concludes that the request has completed. When I first learned about HTTP, my mind was blown. I could finally look under the hood of my browser and understand how the browser is sending different headers to the server and what the server is going to interpret based on the headers that is sent by the browsers. I learned a great deal about HTTP from TCP/IP-Guide.com, which is a great resource to learn about TCP/IP and other web fundamental protocols such as HTTP, SMTP, and so on. I leave a link to the HTTP section on TCP/IP-Guide.com in the description below for you to read it. Okay, so let's continue our adventure with HTTP request smuggling. Just like content length is used to interpret the request body in the HTTP request, there is another header which can be used to tell the server the size of the body in the HTTP request, and that header is the transfer-encoding header. On your screen, you can see 2 HTTP requests. They contain some data in their request body. If you look at the request on the left, it contains the content length header, and this header is set to the value of 11, which means that the request body is supposed to contain 11 bytes. And the request here contains the words hello world. Hello space world makes up 11 characters or 11 bytes of data. So that fulfills the content length size. On the right hand side, you see a header transfer-encoding, which is set to the value of chunk. Just like content length, it is also used for the server to understand how to interpret the request body. Now, transfer-encoding chunk, the chunk encoding, follows a specific syntax which is pretty simple to understand. To understand this syntax better, let's go ahead and look at this request with the CRLF characters visible. As the name suggests, in the chunk encoding scheme, the data is sent by the client in chunks. The chunk encoding body, the chunk encoded message body, starts with a number. As you can see on the screen, it starts with a number, and this number denotes the size of the first chunk of data that the client is sending to the server. So in the case of our example request, the first line contains the number 5. Now this number is followed by a CRLF, and on the next line you have the actual data that is being sent from the client to the server. So the first chunk is 5 bytes in size, which is then followed by CRLF, and the data, that is the word hello, which is 5 characters in length or 5 bytes in size. And this chunk of data is then followed by a CRLF again. This indicates the completion of the first chunk of data. The same pattern will be repeated by the client as long as it wants to send data to the server using the chunk encoding scheme. This can go on for as long as the client wants to send data to the server. So here the second chunk, as you can see on the screen, is 6 bytes in size. This chunk size is followed by a CRLF. On the next line, you have the words space followed by void, which satisfy the chunk size of 6 bytes. This again is followed by CRLF. Now, when the client wants to indicate to the server that it has sent all the data that it had to, it will send a 0 size chunk, and this is indicated by the number 0 followed by 2 CRLFs. As you can see on the screen, at the end of the message, there is a 0 size chunk with 2 CRLFs. This indicates that the client is done sending the data to the server, and now the server can start interpreting the data and sending it to the relevant code block for execution. The most important thing that you need to understand in the chunk encoding scheme is that the chunk size indicated in the request body is actually a hexadecimal number. It's not a decimal number, it's a hexadecimal number. Especially when it comes to creating payloads for HTTP request smuggling, you have to keep this in mind that when you're creating the payload, the chunk encoding size, the chunk size is represented in a hexadecimal format. So now we have looked at both the content length headers and the transfer encoding headers and how these headers can be used to form HTTP requests. But what would happen if we do this? What would happen if an HTTP request contains both the content length header and the transfer encoding header? How is the server supposed to interpret such a request? Is it supposed to do it as per the content length header or as per the transfer encoding header? Let's look at what the RFC has to say about it. RFC 2616 mentions that if the request contains both the transfer encoding header and the content length header, it should ignore the content length header and process the request as per the transfer encoding header. So the transfer encoding header takes precedence over the content length header. So this is what is supposed to happen. The receiving server should drop the content length header from a request that contains both content length and transfer encoding and process the request as the transfer encoding header.
But what would happen if a server does not implement this correctly? What would happen if there is a discrepancy between how the front end processes this request against how the backend does it? Let's go ahead and find out what happens in such a scenario.
Take a look at these two requests on the screen, request 1 and request 2, originating from two different users. As you can see in request 1, you have both the content length header and the transfer encoding header. Let's say that these requests are being sent sequentially to a front end which does not implement HTTP 1.1 RFC 2616 correctly, and it just interprets the message on the basis of the first header it encounters, which in this case is the content length header. This front end then passes both the requests sequentially over an HTTP pipeline to the backend server. Now the backend is an innocent backend server which is implementing the RFC correctly. The backend knows that it is supposed to strip off the content length header if a request contains both the transfer encoding header as well as the content length header. So this is what the backend sees or makes sense of request number 1. When the request number 1 reaches the backend, it starts interpreting the request as per transfer encoding header. And as we know that the transfer encoding HTTP request ends with a 0 size chunk. So the server interprets this request and looks for the 0 size chunk, and when it receives the 0 size chunk, it concludes that the request is completed. But wait a minute, where did the letter G from request 1 go? We know that the request was sent from the front end to the back end containing the letter G because it was interpreted by the front end using the content length header, which was of 16 bytes, and the message was exactly 16 bytes in size. So the G must be somewhere. It wouldn't just disappear in thin air. So to understand where the G went, let's try and mimic the HTTP listener ourselves and understand what the server is doing and where the letter G is being sent. Let us visualize the wire, the backend, how it is interpreting the request that it is receiving from the front end. Here you can see the start of request number 1 is the post method. You have the request line first, first, which ends with a CRLF. What follows after the request line are a sequence of headers. You have the content type header, the host header, the transfer encoding header, and after the transfer encoding header, you see there is a sequence of 2 CRLFs, which indicates that this is the end of the headers, and what follows is the message body. As we saw on the earlier slide, that the backend loses the trailing G from request number 1. We want to know where the trailing G has gone. So for the backend, the request number 1 ends at this point where my mouse is, right? It ends at the point that 0 size chunk ends. But we know that the G is somewhere on the wire. So what happens with the G? So again, let's try and understand what the server is doing. After the listener has completed interpreting request 1 and the request is now on its way to being executed by the relevant code block, the listener is going to wait for the next request. And again, while it is waiting for the next request, it is going to look for a pattern. And the pattern it's going to look for is the request line. So whatever follows after request 1 on the wire, the request line is going to be somewhere over there. So it again starts listening for the request line, and the first chunk of characters that the listener encounters is, it starts with GPOST followed by space, followed by a slash, that's the path, and the HTTP version followed by a CRLF. Now this meets the criteria, the pattern of a request line. So the G, which was lost somewhere by the backend, but it was still on the wire, has somehow gotten attached to request number 2. And so the method of request number 2 has now changed from post to gpost. So this is what the backend will see. So this is classic CLTE poisoning. It is called CLTE because the front end interprets your request on the basis of the content and header, and the backend is interpreting it based on the transfer encoding header. What we see here is a clear case of parser differential. Parser differential turns out to be a root cause in a lot of vulnerabilities. So here, parser differential occurs when two components of one system do not agree with the interpretation of the same information. In our case, what we saw, the front end and back end do not agree with the end of request number 1, and that leads to the poisoning of request 2. Alright, that's enough theory for you. In the next video, we will solve a PortSwigger Academy Lab on request smuggling and try to apply the knowledge that we gathered right now to solve a lab. I hope this video has been helpful to you, and now you have a slightly better understanding about HTTP request smuggling. See you in the next video.